You think you know why water freezes? You've been told it's simple. Cold removes energy. Molecules slow down. The liquid becomes solid. That story feels neat, comfortable, finished. It's also incomplete, because if freezing were just about things slowing down, then water should behave like almost every other substance in the universe. But it doesn't. Water expands when it freezes. Ice floats instead of sinking. And life on Earth exists largely because of this one strange mistake. Physicists didn't miss this. They were disturbed by it. Richard Feynman once said that water is the most studied substance in physics and still full of surprises. So if you think you already understand freezing, good. That's exactly the mindset this topic destroys. One, freezing is not just about cold. Most people imagine freezing as a simple story. Things get cold. Molecules slow down. Eventually they stop, and liquid becomes solid. That explanation feels intuitive. It sounds mechanical, and it's wrong in the most important way. Molecules never stop moving, not at freezing, not even near absolute zero. Motion is built into reality at a fundamental level. Quantum mechanics guarantees it. There is always vibration, always uncertainty, always movement. So if freezing were only about motion slowing down, nothing would ever truly become solid. What actually changes during freezing is not how fast molecules move, but how they are arranged. Freezing is not a speed limit. It's a structural agreement. Think of liquid water as a crowded room where everyone is moving freely. People bump into each other, rotate, shift positions. There are patterns forming for brief moments, but nothing lasts. Bonds form and break constantly. As temperature drops, that chaos doesn't disappear. Instead, it becomes selective. The molecules still move, but now some arrangements last longer than others. Certain positions become energetically favorable. Others become unstable and fall apart quickly. This is where the idea of organization becomes crucial. Water molecules are not featureless balls. They are shaped, polarized, and directional. Each molecule has regions that prefer to be near certain regions of other molecules. When conditions are right, those preferences start to dominate behavior. Cooling gives those preferences more influence, not because motion disappears, but because random motion loses the ability to overpower structure. At higher temperatures, kinetic energy overwhelms organization. Molecules collide too violently to maintain stable arrangements. Bonds form, but they are short-lived. As energy decreases, collisions become gentler. Temporary bonds survive longer. Patterns persist instead of dissolving immediately. Freezing begins when those patterns stop being temporary. This is the moment most people misunderstand. Freezing is not a sudden event where molecules lock up. It's a gradual transition where the balance tips from chaos-dominated behavior to structure-dominated behavior. Water molecules begin testing configurations. They form small clusters. Those clusters dissolve. Others form again. Some last slightly longer. Each cycle is a negotiation between energy and geometry. The system keeps searching for an arrangement that minimizes total energy while respecting molecular shape and bonding rules. Eventually, one structure wins. Not because it is perfect. Not because it is compact, but because it is stable enough to survive. And here's the counterintuitive part. The structure water chooses inefficient. Most substances freeze into tightly packed solids. Their molecules squeeze closer together. Density increases. Water means compression. Water rejects that strategy because of its bent shape and hydrogen bonding preferences. Water molecules arrange themselves into an open lattice. This lattice prioritizes bonding angles over packing efficiency. That choice lowers energy locally, but wastes space globally. So the solid form of water occupies more volume than the liquid form. This is not what cold wants to do. This is what molecular geometry forces it to do. That's why saying cold makes water freeze is an oversimplification. Cold doesn't instruct water. Cold only removes options. When thermal energy drops low enough, water molecules can no longer ignore their shape. They must obey it. Freezing is the moment geometry takes control. This also explains why freezing doesn't happen at a single perfectly sharp temperature in real systems. Impurities, pressure differences, and surface effects all influence how easily a stable structure can form. In very pure water, freezing can be delayed below the normal freezing point. This is called supercooling. The molecules are cold enough, but they haven't yet found a stable organizational seed. The moment such a seed appears, freezing propagates rapidly. This shows you something important. Temperature alone does not cause freezing. Structure does. Temperature only determines whether structure is allowed to persist. Once the structure begins forming, it reinforces itself. Each molecule that locks into place makes it easier for the next one to do the same. Order spreads, not because motion stops, but because motion becomes constrained. This is why solids are rigid, even though their molecules are still vibrating. The vibrations happen around fixed positions, not through free movement. So when you hold ice in your hand, you are not holding stillness. You are holding organized motion. This distinction matters far beyond water. It applies to crystals, metals, biological tissues, and even systems that aren't physical in the usual sense. Economies, habits, and beliefs also freeze when structure becomes dominant over randomness. Water freezing is one of the clearest physical demonstrations of this principle. Order does not require immobility. Order requires constraints. And water chooses a very strange set of constraints. It chooses angles over efficiency, bonds over compression, stability over density. That choice is why ice floats. That choice is why lakes freeze from the top. That choice is why life survives winter. But none of that was the goal. Freezing is not kindness. It is compliance. Water is obeying its geometry. And once you understand that freezing is about organization rather than cold, you start to see the world differently. Because everywhere you look, what appears solid, fixed, or permanent is often just motion that has learned where it is allowed to exist. Water molecules are shaped like a problem. At first glance, a water molecule looks boring. 2 hydrogen atoms, 1 oxygen atom. Simple chemistry. End of story. That assumption is the second trap, because the behavior of water has almost nothing to do with what it's made of, and almost everything to do with how it's shaped. If water molecules were straight, symmetrical, and evenly balanced, freezing would be boring. Ice would sink, lakes would freeze solid, life would struggle. But water molecules are bent. Not slightly, not accidentally, fundamentally bent. The oxygen atom pulls electrons toward itself more strongly than hydrogen does. This creates an uneven distribution of charge. One side of the molecule becomes slightly negative, the other slightly positive. So every single water molecule becomes a tiny electrical object with orientation. This destroys the idea that molecules are just neutral dots bouncing around. Water molecules have direction. They care how they face each other. They react differently depending on angle. This is where everything starts to go wrong in the best possible way. Because once a molecule has direction, motion is no longer random, it becomes conditional. When 2 water molecules come close, the positive side of one is attracted to the negative side of another. This attraction is called a hydrogen bond. It's weaker than a chemical bond, but much stronger than a random collision. Here's the key mistake people make. They imagine hydrogen bonds as rigid connections. They're not. Hydrogen bonds form, break, rotate, and reform constantly in liquid water. At any moment, a water molecule may be bonded to several neighbors, briefly. This creates a dynamic network, not a static one. Liquid water is not chaos. It's organized instability. Now add cooling. As temperature drops, molecular motion becomes less violent, not motionless, less disruptive. This gives hydrogen bonds more time to exist before being broken. And once bonds last longer, geometry starts to matter more. Water molecules prefer specific angles when bonding. These angles are not arbitrary. They come from the quantum structure of the molecule itself. The preferred arrangement creates a roughly tetrahedral geometry around each molecule. That geometry does not allow close packing. This is the problem. If water molecules tried to pack tightly like spheres, they would have to break their preferred bonding angles. That would raise energy. So water faces a trade-off. Pack efficiently and increase energy, or waste space and lower energy. Water chooses wasted space. This is not a philosophical decision. It is a physical necessity dictated by shape. As freezing begins, molecules increasingly commit to these preferred angles. Temporary clusters become more regular. Randomness loses influence. Eventually, the system settles into a repeating pattern where each molecule satisfies as many hydrogen bonds as possible without violating geometry. That pattern is hexagonal, and hexagonal structures are spacious. This is why ice has holes in it at the molecular level. Not literal holes you can see, but empty regions where molecules could have been if packing were the priority. Most substances minimize volume when freezing. Water maximizes bonding satisfaction. This is why water behaves like a problem substance in physics. It refuses to act like an ideal material. It refuses to simplify. Even small changes in temperature or pressure can dramatically alter how water molecules organize themselves. That's why there are many types of ice. Different pressures force different compromises between bonding and packing. Under enough pressure, water molecules abandon their spacious arrangement and pack more tightly, forming denser ice phases. But under normal conditions, geometry wins. And here's the deeper implication. The shape of water molecules does not just affect freezing. It affects surface tension, heat capacity, solvent behavior, and biological chemistry. Water's ability to dissolve substances, transport nutrients, and stabilize proteins all trace back to the same molecular asymmetry. The same bent shape that makes ice float also makes blood flow, cells function, and life persist. This is why reducing water to H2O is misleading. That formula tells you composition. It tells you nothing about behavior. Behavior comes from structure, and structure comes from shape. If water molecules were linear instead of bent, hydrogen bonding would behave differently. The freezing structure would change. Density relationships would flip. The entire thermal behavior of Earth would shift. Glaciers, oceans, weather systems, all of it depends on this one geometric quirk. So when physicists say water is strange, they don't mean mysterious in a mystical sense. They mean structurally inconvenient. It breaks simple models. It resists elegant equations. It forces complexity where simplicity should exist. And all of that begins with shape. Freezing is not just molecules deciding to line up. It is molecules being forced to respect geometry. They cannot escape. Once you understand that, freezing stops looking like a temperature problem and starts looking like a spatial one. Water freezes the way it does because it has no other option. Its shape makes sure of that. Ice is an expansion, not a collapse. This is the moment where intuition completely fails. You've been trained to believe one simple rule. When something freezes, it shrinks. The solid form should be tighter, heavier, and denser than the liquid. That rule works almost everywhere. Metal contracts when it solidifies. Rock becomes dense. Most liquids sink when frozen. Water breaks the rule so badly that it reshapes the planet. When water freezes, it expands. Not because it wants to, not because cold pushes it outward, but because the structure it chooses cannot fit into a smaller space. To understand this, you have to stop thinking in terms of temperature and start thinking in terms of architecture. As water cools, hydrogen bonds stop being temporary suggestions and start becoming commitments. Molecules lock into preferred angles. Those angles force each molecule to keep its neighbors at a distance. The result is a rigid lattice. This lattice is not tight. It is open. It is spacious. Imagine building a structure out of rigid sticks that can only connect at fixed angles. No matter how much you try to compress it, empty space remains. The structure resists collapse not because it's strong, but because geometry forbids closeness. That is ice. In liquid water, molecules slide past one another. They momentarily adopt structured arrangements, but those arrangements collapse under constant motion. Molecules can slip into gaps, increasing density. In ice, those gaps are locked in. Freezing does not squeeze water together. It freezes space itself into the structure. This is why ice occupies more volume than the same amount of liquid water. And this single fact changes everything. Because density determines destiny. Ice is less dense than liquid water, so it floats. That sounds trivial until you follow the consequences. When ice forms on the surface of a lake, it creates an insulating layer. The ice slows heat loss from the water below. This prevents the entire body of water from freezing solid. Fish survived because ice floats. If ice sank, lakes would freeze from the bottom up. Each winter would add another layer of ice on the lake floor. Over time, bodies of water would become permanently frozen. Life would not recover. This is not a small advantage. It is a planetary condition. Water's expansion during freezing stabilizes climate, preserves ecosystems, and moderates temperature extremes. And none of it was planned. This behavior emerges from molecular compromise, not purpose. Water does not optimize for survival. It optimizes for bonding. The hexagonal lattice of ice is simply the lowest energy solution available under normal conditions. The fact that this solution happens to protect life is coincidence layered on top of necessity. That's uncomfortable for people who like tidy explanations, because it means existence is balanced on structural accidents. The expansion of water during freezing also explains why rocks crack, pipes burst, and roads fracture in winter. When water seeps into small spaces and freezes, it expands with enormous force. That force comes not from pressure applied by cold, but from geometry refusing compression. Space is not pushing outward aggressively. It is passively occupying more space than its container allows. The container breaks. This tells you something subtle but important. Expansion during freezing is not an energetic explosion. It is a spatial incompatibility. Ice doesn't push. It refuses to fit. This refusal is powerful enough to split stone, and it exists because water molecules care more about angle than proximity. Most substances collapse into denser arrangements when freezing because their molecules don't mind crowding. They are shaped in ways that allow efficient packing. Water molecules are not. Their hydrogen bonds demand spacing. Their geometry enforces distance. So freezing water is not a collapse into order. It is an expansion into constraint. This also explains why ice is relatively soft and brittle compared to many solids. The open lattice leaves fewer connections per unit volume. The structure is stable, but not compact. You can crush ice more easily than metal because ice has room to fail. This openness also explains why ice melts the way it does. As soon as thermal motion disrupts the lattice, molecules immediately slip into closer arrangements. Density increases, volume decreases. Liquid water is what happens when the lattice collapses under motion. So melting is not just adding heat, it is removing geometric discipline. This perspective changes how you think about phase changes. Freezing is not matter becoming rigid. It is matter accepting rules. Rules about where it may sit. Rules about how it may connect. Rules about how much space it must occupy. Ice follows those rules even when they cause expansion, weakness, or instability. And this is why physicists pay attention to water. Not because it's mystical, but because it disobeys expectations in a way that reveals deeper laws. Water reminds you that nature does not prioritize simplicity, efficiency, or intuition. It prioritizes constraint satisfaction. The expansion of ice is not a special exception, inserted into physics. It is the honest outcome of shape, bonding, and energy minimization colliding. And the fact that life depends on that collision is the real shock, because it means the difference between a living planet and a frozen one came down to how a molecule refuses to pack tightly when it freezes. That's not poetry. That's structure deciding fate. Floor temperature does not control freezing alone. One of the most stubborn misunderstandings about freezing is the belief that temperature is the boss. Cold comes in, the molecules slow down. Freezing happens. That mental model is comforting because it's linear, because it leads to effect. One dial controls the outcome. Reality is not that polite. Temperature is only one variable in a crowded room of constraints. Freezing happens when all conditions align, not when a thermometer hits a specific number. This is why water can remain liquid below its normal freezing point. Pure, undisturbed water can be cooled several degrees below zero and still refuse to freeze. This isn't magic. It's called supercooling, and it exposes a critical truth. Cold alone does not force freezing. What freezing requires is not just low energy, but a starting structure. For ice to form, water molecules must first assemble a small, stable cluster arranged in the correct geometry. This cluster acts as a template. Once it exists, surrounding molecules can attach more easily and freezing spreads rapidly. Without that initial structure, nothing happens. The water is cold enough, the energy is low enough, but the organization hasn't begun. So the liquid waits. This tells you something uncomfortable. Freezing is delayed, not by warmth, but by indecision. The system is stuck searching for a configuration that satisfies all constraints at once. Until it finds one, liquid behavior continues even in conditions where ice should exist. Now add pressure. Pressure changes everything. Squeeze water hard enough, and its freezing behavior flips. Under high pressure, water molecules are forced closer together. The spacious hexagonal lattice becomes energetically unfavorable. So water adapts. It forms different kinds of ice. Not one.
Penny.
Some of these ice phases are denser than liquid water. Some sink. Some only exist deep inside planets or beneath glaciers where pressures are extreme. This alone should destroy the idea that freezing is a single event with a single outcome. Freezing is not a rule. It's a negotiation. Temperature, pressure, impurities, surfaces, and molecular motion all contribute to the final structure. This is why freezing water in a freezer doesn't always produce the same ice. Crystals form differently, depending on how quickly energy is removed, where nucleation starts, and how impurities influence bonding. Fast freezing traps disorder. Slow freezing allows structure to refine itself. This is why clear ice forms when freezing is controlled and gradual. The molecules have time to organize properly, pushing impurities aside. Disorder is excluded as order takes over. Freezing is selective. It does not accept everything equally. Now consider surfaces. Water freezes more easily when it touches something rough or structured. Dust particles, scratches, or container walls give molecules a place to begin organizing. These surfaces act as scaffolding. They reduce the energy cost of forming that initial ice cluster. Without them, freezing resists. This is why clouds can remain liquid well below freezing temperatures. Tiny droplets float without surfaces to organize around. When freezing finally starts, it can happen explosively. Again, temperature was never the only factor. This has broader implications. If temperature truly controlled phase alone, materials would behave predictably everywhere. They don't. Structure decides behavior. Constraints decide outcomes. Temperature only sets the stage. Water is especially sensitive because its bonding rules are strict and its geometry is unforgiving. Small changes in conditions create large changes in organization. This sensitivity is why climate systems are fragile. Ice formation affects reflectivity, heat retention, and circulation. Small structural shifts at the molecular level cascade into planetary effects. Freezing is not just a physical event. It is a systems event. And here's the deeper point most people miss. When we reduce freezing to temperature, we train ourselves to ignore complexity. We assume control exists where it doesn't. This is why simplified models fail when conditions change. Water doesn't follow instructions. It responds to constraints. Cold does not command freezing. It merely removes resistance. Freezing occurs when structure becomes inevitable. Once you see this, you stop asking how cold does it need to be and start asking what structure is allowed to exist here. That shift matters because it's the same mistake people make when they assume pressure alone causes collapse or energy alone causes change. Systems don't obey single variables. They obey relationships. Water freezing teaches this lesson brutally well. You can lower temperature all you want. If structure cannot begin, nothing happens. And the moment structure appears, everything changes at once. That's not how simple rules behave. That's how reality behaves when geometry, energy, and probability collide. Freezing is not temperature winning. It's structure finally getting permission to exist. 5. Simplicity fails where water begins. Physicists love simple systems. They love problems where you can isolate a variable, write an equation, and predict what happens next. Gases behave nicely. Ideal solids behave nicely. Even many liquids can be approximated without too much embarrassment. Water refuses this cooperation, not because it's complicated in composition, but because it is complicated in behavior. Water is one of the most studied substances in science, and yet it continues to resist complete theoretical description. That alone should make you suspicious of any explanation that sounds finished. The problem is not lack of effort. The problem is emergence. Water does not behave like a collection of independent molecules. It behaves like a network. Each molecule interacts with several neighbors through hydrogen bonds. Those bonds constantly form, break, rotate, and reform. The state of one molecule influences the possibilities of the next. This creates feedback. Small local changes propagate. Temporary patterns influence future structure. History matters. Simple models assume independence. Water does not grant that assumption. In liquid water, molecules are always in motion, but that motion is constrained by a shifting web of relationships. The liquid is neither ordered nor random. It exists in between. That middle ground is where equations struggle. When water freezes, the difficulty intensifies. The transition is not just about losing energy. It is about selecting one structure out of many possible arrangements. That selection depends on local fluctuations, impurities, pressure, and geometry. The path to freezing matters as much as the final state. This is why two identical samples of water can freeze differently under slightly different conditions. One forms large, clean crystals. Another traps disorder. Another delays freezing entirely. Simple rules cannot account for this sensitivity. Water forces physicists to confront a painful truth. Knowing the laws does not guarantee understanding the outcome. The equations governing water molecules are known. The interactions are understood at a basic level. And yet, predicting collective behavior remains difficult. This is not failure. It is a boundary. Water sits at the edge where reductionism starts to break. Reductionism works when the whole is just the sum of its parts. Water is not like that. The whole creates new behavior. The parts do not exhibit alone. A single water molecule does not expand when frozen. A network of them does. That distinction matters. The freezing of water demonstrates emergence in its purest form. No molecule knows it is building ice. No molecule intends to create a lattice. The structure arises because local rules, applied repeatedly, constrain global possibilities. This is why water challenges intuition. You expect matter to behave smoothly as conditions change. Water responds abruptly. Small temperature shifts trigger large structural reconfigurations. These phase transitions are not gradual. They are thresholds. On one side, motion dominates. On the other, structure dominates. Between them, behavior becomes unstable and difficult to model. This instability is not unique to water, but water makes it obvious. Many systems behave this way: traffic jams, financial crashes, ecosystem collapses. They look stable until they aren't. Small perturbations trigger large reorganizations. Water freezing is a physical example of this phenomenon, and it reveals why simplicity fails. When interactions are local but consequences are global, prediction becomes hard. Linear thinking collapses. Cause and effect stop lining up neatly. This is why physicists still debate the details of water's behavior under extreme conditions. New phases of ice continue to be discovered. Anomalies persist. Water is ordinary in appearance, but extreme in consequence. This matters because it forces humility. If we cannot fully tame water, a substance we drink, freeze, and boil daily, then confidence in our understanding of more complex systems should be cautious. Water reminds science that elegance has limits. Not everything compresses into a clean formula. Not everything yields to intuition. Some systems demand patience, approximation, and acceptance of uncertainty. Freezing is where this lesson becomes visible. What looks like a simple transition hides a web of interactions too dense for single variable explanations. Water does not freeze because a rule says so. It freezes because countless local constraints converge into one allowed structure. And once that structure appears, simplicity disappears. That is why water unsettles physicists, not because it's mystical, but because it exposes the edge of understanding. And standing at that edge is uncomfortable for anyone who prefers clean answers. Water doesn't offer them. It offers reality instead. Nature does not care about life, only about energy. This is the lesson people resist the most, because it strips away comfort. When people learn that ice floats, that lakes don't freeze solid, that life survives winter because of how water freezes, they instinctively reach for meaning, purpose, desire. They want water to be benevolent. Physics does not allow that story. Water does not protect life. Water does not preserve ecosystems. Water does not care. Water follows energy. Every structure water adopts is the result of one brutal rule: minimize total energy under given constraints. That's it. No foresight, no intention, no concern for consequences. The hexagonal structure of ice exists because under normal Earth conditions, it allows water molecules to satisfy the maximum number of hydrogen bonds while keeping energy low. The fact that this structure happens to float is incidental. Life adapted to water's behavior. Water did not adapt to life. This distinction matters more than people realize, because it corrects a dangerous misunderstanding about nature. Nature does not optimize for outcomes. It optimizes for constraints. Energy, geometry, pressure, and probability dictate what is allowed. Everything else is fallout. When water freezes, it is not choosing the best structure in a moral or functional sense. It is choosing the only structure that survives under those rules. And that structure just happens to create conditions where life can persist. If the rules were slightly different, the outcome would be catastrophic, and nature would not hesitate. Consider how narrow the margins are. A small change in molecular angle, bonding strength, or charge distribution would alter ice density. Ice could sink. Oceans could freeze solid. Climate could collapse. Physics would not intervene to fix it. There is no safety net. This should recalibrate how you think about natural order. The world is not balanced because it must be. It is balanced because it happens to be. Water freezing illustrates this ruthlessly. The same process that keeps fish alive also splits rocks, destroys roads, and bursts steel pipes. The same expansion that stabilizes climate also erodes mountains. There is no preference, but only consequence. When people say nature is wise, they are projecting meaning onto mechanics. Nature is consistent, not kind. Water expands during freezing because its geometry forces it to. If that expansion crushes something, so be it. If it preserves something, so be it. This neutrality is uncomfortable, but it is honest. And it leads to a deeper insight. Life exists not because the universe supports it, but because life found a narrow set of conditions it could exploit. Water freezing the way it does is one of those conditions. Not a gift. A coincidence. A stable coincidence, but a coincidence nonetheless. This perspective also explains why extreme environments exist, where water behaves very differently. Under enough pressure, water abandons its familiar ice structure and forms denser phases that would be hostile to life. Deep beneath ice sheets or inside large planets, water does not behave gently. It obeys pressure without compromise. The rules didn't change. The conditions did. That's the lesson. Water's behavior is not anchored to outcomes we value. It is anchored to physics. But physics is indifferent. This is why scientific explanations feel cold to people who want reassurance. They don't tell you that things happen for a reason. They tell you that things happen because they must. Freezing happens when energy minimization allows structure. Expansion happens when geometry demands space. Floating happens when density drops. Life survives if it fits into that framework. If it doesn't, it ends. Water freezing teaches you to stop anthropomorphizing reality. The universe is not hostile. It is not friendly. It is uninterested. And that is precisely why understanding it matters. Because survival, stability, and progress don't come from assuming the world will cooperate. They come from learning the rules well enough to work within them. Life didn't argue with water's freezing behavior. It adapted to it. Fish evolved antifreeze proteins. Plants adapted to ice formation. Ecosystems learned to operate around seasonal freezing. None of this required water to care. It required life to pay attention. That is the real power of this lesson. Understanding water freezing the way it does is not about marveling at nature's generosity. It's about recognizing how fragile stability actually is. The world works because constraints line up for now. And the moment they don't, nothing in physics promises a rescue. Water freezing is not comforting. It is clarifying. It shows you a universe that runs on rules, not mercy. And paradoxically, that truth is what allows intelligent life to exist at all. Because only in a rule-bound universe can adaptation succeed. Water doesn't support life. Life survives water. 7. The real shock is how little we question the ordinary. By the time you reach this point, the physics itself is no longer the most disturbing part. The disturbing part is how long you lived around ice without ever asking why it behaves this way. You drink water, you watch it freeze, you put ice in a glass, and your brain files all of it under normal. That familiarity is the real blind spot, because nothing about water freezing is obvious. Nothing about it had to be this way, and yet, once something becomes routine, the mind stops interrogating it. This is not a failure of intelligence. It's a feature of survival. The brain is designed to conserve effort. It does not spend energy questioning stable patterns unless something breaks. As long as ice floats and winters pass without catastrophe, curiosity shuts down. But science advances only when that shutdown is overridden. Physicists like Richard Feynman were famous not because they knew more facts than everyone else, but because they refused to stop being confused by ordinary things. Feynman didn't look at water and see H2O behaving correctly. He saw an anomaly that demanded explanation. Why should freezing make something expand? Why should a solid be less dense than its liquid? Why should this behavior be so crucial for life? Those questions sound childish. They are not. They are dangerous because they attack assumptions that feel settled. Most people assume understanding exists because names exist. You call it freezing, so you think you know what's happening. You call it ice, so you assume it's just another solid. Language creates false closure. Once something has a label, inquiry stops. Water freezing teaches you how misleading that can be. The word cold hides complexity. The word solid hides motion. The word normal hides improbability. Ice floating is not normal. It is rare. Only a few substances behave this way. Most sink when frozen. Most collapse into denser forms. Those oceans are balanced on an exception. And because that exception repeats daily, it disappears into the background. This is how deep ignorance survives next to constant exposure. You don't question what doesn't threaten you. The shock is not that water behaves strangely. The shock is that we stop noticing. This extends far beyond physics. Everything stable feels inevitable in hindsight. Climate, ecosystems, even social systems appear permanent until they fail. Only collapse renews curiosity. Water freezing is a quiet reminder that stability is not guaranteed by necessity. It is maintained by conditions. Change the conditions and normal disappears. What makes this lesson powerful is that it forces intellectual humility. If something as common as ice can hide so much complexity, then how much complexity is hiding in things we take even more for granted? Time, consciousness, matter itself. The danger is not ignorance. The danger is unexamined familiarity. When you stop asking why, you stop learning. When you stop learning, you mistake stability for permanence. Feynman's real lesson was not about water. It was about attention. He treated the everyday as suspicious. He assumed that if something worked too smoothly, it probably hid deeper rules. That mindset is rare. Most people wait for novelty to trigger curiosity. Feynman used boredom as a signal that something important was being overlooked. Water freezing is boring only because it's constant. Strip away that constancy, and you see how precarious the arrangement really is. A slight change in molecular angle, bonding strength, or environmental pressure would turn ice into a threat instead of a shield. And nothing in physics would stop it. This is not meant to frighten you. It's meant to sharpen you. The universe does not announce its miracles. It buries them in repetition. Ice floating in a glass is one of those buried miracles. Not because it's magical, but because it works at all. Understanding that should change how you look at ordinary things. Not with awe, with suspicion. Because the more something feels obvious, the more likely it is that you haven't looked closely enough. Water freezing is not a solved curiosity. It is a daily reminder that reality does not explain itself unless you demand answers. And the moment you stop demanding, you stop understanding. That is the real shock. Not that water freezes strangely, but that we learn to stop asking why. So when you look at ice now, you should feel a quiet discomfort. Not wonder, not comfort. Discomfort, because what you're seeing is not a simple consequence of cold. It's the outcome of geometry, energy and constraint aligning just well enough to hold a planet together. Nothing about it was guaranteed. Water did not freeze this way because it had to support life. Life survived because water happened to freeze this way. Reverse that order and the story collapses. That should change how you think about normal. Normal is not safe. Normal is not permanent. Normal is just a temporary agreement between conditions. Ice floating, oceans staying liquid beneath winter, ecosystems surviving year after year. These are not laws. They are balances. Balances can break. The real lesson in water freezing is not scientific trivia. It's intellectual discipline. If something this ordinary can hide this much complexity, then the world is far less understood than it appears. Familiarity is not knowledge. Repetition is not explanation. Understanding begins the moment you stop accepting everyday things as obvious. Water freezing is not a solved fact. It's a warning disguised as routine. And once you see that, you don't just understand ice better. You understand reality more honestly.